Right now, there are millions of rocky bodies crisscrossing the inner solar system. Many of these orbital paths bring them uncomfortably close to Earth's neighborhood. Recognizing this constant traffic, Congress passed a mandate in 2005 requiring NASA to discover at least 90 seconds. It blinds us to objects approaching from the sun, lost in daylight glare. In 2022, multiple U.S. agencies gathered for the 4th Planetary Defense Tabletop exercise to simulate a short-warning asteroid impact. The after-action report identified a critical vulnerability. Our inability to detect these obscure asteroids early makes an effective national response almost impossible. Solving this intelligence failure requires 2 structural changes to our approach. We have to abandon optical light entirely, and we have to move our observation posts beyond Earth's atmosphere. This is the exact engineering objective behind the NEO Surveyor space telescope. Instead of operating on the ground, it is designed to travel 1 million miles away from Earth, heading directly toward the Sun. Its destination is the Sun-Earth L1 point, a stable region where the spacecraft maintains a fixed position. This removes atmospheric distortion and prevents lunar interference. From here, NEO Surveyor looks back toward Earth's orbit, scanning near-Sun regions that blind ground observatories. By physically changing where we look from, the telescope mathematically eliminates the geometric blind spots of the inner solar system. Instead of searching for reflected optical light, NEO Surveyor uses heat-sensitive channels engineered to detect the thermal infrared heat emitted by asteroids themselves. To keep its own heat from interfering with the highly sensitive infrared detectors, the spacecraft uses passive cooling radiators and a massive 6.15-meter sunshade. Once in position, the telescope organizes its continuous sky scanning into a core operational unit known as a visit. A single visit takes 3 minutes. The telescope captures 6 dithered exposures in a hexagonal pattern, measuring thermal output. Repeating this daily creates a cadence, building observational tracks over 10 days to confirm exact trajectories. Because these objects absorb sunlight and heat up, thermal imaging weaponizes an asteroid's darkest camouflage, turning the most invisible threats into the most obvious targets. Capturing these infrared images is only the first step. The raw data requires continuous mathematical analysis back on the ground. Every day, NEO Surveyor downlinks its data, feeding it directly to the Minor Planet Center and the Center for Near-Earth Object Studies at JPL. Analysts process this thermal data to compute high-precision asteroid orbits, calculating the object's speed, rotation, and exact probability of impacting Earth. By observing these objects across multiple epochs, tracking them over months and years, scientists can predict their exact paths decades or even a century into the future. NEO Surveyor serves as the raw mathematical fuel for an international probability engine built to accurately forecast the layout of the inner solar system. The management of this global early warning architecture is led by NASA's Planetary Defense Coordination Office. When an orbital track shows a probable collision decades in advance, we have time to mount real mitigation missions. We can build and launch kinetic impactors, like the DART mission, to intentionally strike the asteroid and alter its orbit. In the strict physics of planetary defense, raw destructive power and advanced rocketry are entirely useless without the luxury of time to deploy them. Ultimate success in planetary defense doesn't rely on a dramatic scramble. It relies on quiet, continuous observation, ensuring these disasters never happen at all.